In this video, we're going to look at the chapter review for Chapter 7, which is Section 7.7. As I've done in the previous videos, I'm going to set this lesson up sort of to help guide you in preparation for your exam. So the first thing I want to comment on is one of the sections in Chapter 7, 7.6, the inverse trig functions. That is a topic that is not part of this course. So you are not responsible for anything in Section 7.6. The way I'm going to set the exam up, we basically studied two categories of functions in this unit. We studied the exponential and logarithmic functions, and then we studied the trigonometric functions. I'm going to set your exam up in two parts. So part A will be the first functions that we studied in this unit, the logarithmic and the exponential. And again, I want to stress that I think it's really important that you understand exactly what to expect on your exam. So I'm going to set up the examples that I'm going to do here, the review, precisely the way it'll be on your exam so that you know exactly what my expectations are of you. So under the category of logs and exponents, the first thing I want you to be able to do is I want you to be able to simply show me that you have an understanding of logs. I want you to be able to evaluate logs and exponents. And what do I mean by that? For example, if I gave you something like, what is log base 25 of 5? The purpose of a question like that is I'm just wanting to know, do you understand what a logarithm is? And of course, a logarithm is an exponent. So what this question is asking is if you took the base 25, so if you took the number 25, what exponent would you have to raise it to get the argument, the answer inside the log? So if you were to convert this to its exponential form, it would be 25 to what exponent is 5? Well, to get 25 to be 5, you have to take a square root. And a square root, of course, is 1/2. So this answer would be 1/2. Now you'll notice that this question I used the base 25. Another comment I made here on the video is that you were introduced to a new number in this unit, the number e. There will be a distinct emphasis on the number e on your exam. In fact, when it comes to taking derivatives, you'll only be responsible for derivatives of the natural log and the natural exponential functions. There will be very few questions on this exam that are of a base that's not e. There might be one or two questions on this section where you're evaluating logs, but I want to make sure you understand that you should not be spending an awful lot of time, especially with the calculus part, on the base of 2 or base of 3. You should be concentrating solely on base e. So for example, using base e, another question I might ask you is, what's the natural log of e cubed? This question, of course, is similar to this one, except the base, in this case, is the number e. Remember that when you have the natural log symbol ln, that really means log base e of e cubed. So again, all I'm really trying to test you on in this part of the exam is, do you get the basic concept of a logarithm? This is asking, what exponent would you raise e to get the answer e cubed? So obviously the answer would be 3. There also might be something like, what's the log base 2 of -8? The reason for a question like this one is, I want you to understand that logarithms only apply for positive values inside the argument. What that question is saying is 2 to what exponent is -8? And I hope that you have enough understanding of exponents and logarithms to realize that that's a mathematical impossibility. You cannot take the number 2 and raise it to an exponent and get a negative answer. If you take the number 2 and raise it to a negative exponent, you'll get a fraction, not a negative answer. So this is a mathematical impossibility. So this is not possible. You can't take the logarithm of 0 or the logarithm of a negative number. Okay, so the first part of the exam will simply be asking the question, do you get the basic concept of a logarithm? And again, I'm just trying to be very helpful here. So your exam will have a question just like this one where it'll say evaluate the following logs and exponential expressions. and you'll have to show me that you understand that. The next thing that we studied with logarithms is I want to make sure that you have an understanding of your properties of logs. There's basically three properties of logs: the log of a product, the log of a quotient, and the power rule. And what I will do is have you show me your understanding of those properties by giving you questions like something like the natural log of 10 plus the natural log of 3, and the instruction would be something like write as a single logarithm. So what I'm getting at here is, do you understand that when you add logs, it's the same as if you take the log of their product? So the natural log of 10 plus the natural log of 3 is really the equivalent expression as the natural log of 30, using our addition rule of logarithms. Another example that combines the other two laws, if you had 3 log 2 minus 2 log 5, and I wanted you to write that as a single logarithm. This question is showing you the other two properties of logs. If you have a number in front of a logarithm, a product, that number becomes the power of the argument. So this would be the log of 2 cubed. You'll notice that this logarithm is not the natural log, and because it doesn't have a base, this is called the common logarithm, or base 10. This would be minus the log of 5 squared, which would give us the log of 8 minus the log of 25. And when you subtract logs, you divide the arguments. So this would simplify to the log of 8 over 25. So the purpose of the second part of the review here is that often when working with logarithms, we need to apply their properties. And I just want you to show me on your exam whether you have a basic understanding of the three properties. The next thing that I want you to be able to do with logs and exponents would be able to solve equations that include logarithmic and exponential functions. And again, you'll notice that the two examples I've selected are both base E. Again, I want to stress that that will be the emphasis on the test. So if you look at the first question, 3a, 3a is an example of a logarithmic equation. A logarithmic equation is when the variable that you're trying to solve for is inside the logarithm, or in other words, it's the argument. The way that you solve logarithmic equations is actually a couple strategies. With this one, you simply convert it back to its exponential form. So this really means that you have log base E of x equals 3. So if I convert that back to its exponential form, the base is E, the exponent is 3, and that's equal to x. And we're finished. The answer to that equation would be the number E cubed. Now, E cubed is an irrational number. You can actually work it out on your calculator. It's approximately 2.718 cubed. But I don't see any reason why you'd want to do that. It's better and faster just to leave the answer as E cubed. Just like in trig we leave the number pi often as a symbol, you really should leave the number E as a symbol as well. So I would like you just to leave the answer as E cubed. The second question is an exponential equation. The variable we're trying to solve for is in the exponent. And just like with the logarithms, the way you solve this type of equation is you simply write it in its appropriate form, the appropriate form being its counterpart. So we're going to convert this into a logarithm. So this would be a logarithm of base E. And of course, the answer to a logarithm is an exponent. So this is going to be log base E. So just like over here, we had log base E of x equals 3, which converts to e to the 3. So the answer to a logarithm is always the exponent. So this is going to be log base E of 2 equals x plus 3. The answer to a logarithm is always the exponent. Now, log base E is really just the natural log of 2 equals x plus 3. Now again, the natural log of 2 is just a number. That would be e to some exponent that equals 2. It'd be a little bit less than 1. There really is no reason to change it to a decimal. You can on your calculator just type in the natural log of 2 and you'll get a decimal value, but why not just leave it as the natural log of 2? Subtract 3 from both sides and your answer would just be the natural log of 2 subtract 3. Okay, so that's basically a bit of a review on how to solve exponential and logarithmic equations with the emphasis on base E. Now the next thing, once we were done working with, so you'll notice that the first 3 sections were just basically getting at your understanding of logs and exponents. Now we got into the actual calculus part. And the calculus part, of course, is something that will appear on your exam, and that would be your ability to differentiate. So the next thing that I would have you do is differentiate the following functions. And as I often do on your exams, I don't want you to be concerned about simplifying. Often we do have to simplify derivatives if we want to do an application, but if my goal is to test you on your knowledge of taking derivatives, I don't need to see you simplify it. So on your exam, you will not be asked to do the simplifying, and so you shouldn't be worrying about that as far as your preparation. So we'll do a few examples. For example, if I had a function f of x equals the natural log of x minus 4. Okay, so really what this is getting at is, do you know the basic rule? There's a rule for taking the derivatives of the natural log. The rule is that the derivative is 1 over the argument. So the derivative here, f prime, would be 1 over the argument x minus 4. And then remember that you always have to multiply by the derivative of the argument. So you'd have to multiply by the derivative of x minus 4. Well, in this case, it's just 1, so it doesn't affect our answer. So the answer would just be 1 over x minus 4. Another example, we could have the function f of x equals the natural log of the cube root of x. Now, the reason why I've selected this example is, if you recall, first of all, we need to change this to an exponent. So this would be the natural log of x to the 1/3. Now we could leave the x to the 1/3 alone there, and we could just use our rule that we used over here. We could go 1 over x to the 1/3 and then take the derivative of x to the 1/3. But because of the fractions, it gets kind of awkward. So you may recall that because it's a logarithm, let's take advantage of that. When you have a power inside of a logarithm, that power can be written in front. So the natural log of x to the 1/3 is really just the same thing as 1/3 times the natural log of x. Now taking the derivative is a very simple process. The 1/3 is a constant, it just stays out front. And when we take the derivative of the natural log of x, we just get 1 over x. So our answer would just be 1 over 3x. Now if you happen to do this question the other way, if you actually did it without moving the 1/3 out front, your answer would end up being quite a complicated expression. In that case, I'd have a difficult time giving you full credit for it, because that expression could be simplified into something obviously, like in this case, 1 over 3x. So please take advantage of the fact that you have logarithms and use your properties. We could involve other rules that we've taken this year. We could have something like 3x times the natural log of 2x. I show you this one just to remind you that even though we're studying logs and exponents, that all the rules we've taken this year still apply. 3x is a function, and that function is being multiplied by a natural log function. So we have a product rule. So our derivative here, f prime, would be the derivative of 3x, which is 3, times the natural log of 2x, plus the derivative of the natural log of 2x, which would be 1 over the argument, times the derivative of the argument, which would be 2, times the first function, which would be 3x. Now you'll notice that I have said do not simplify. So if you got an answer like that one, I do not expect you to do any simplifying. You will get full credit for that. Now obviously there is some simplifying that can happen there, and some fairly simple work. We could just, for example, cross off these 2's. We could take out a common factor of 3. but these are things that you would not be expected to do to get full credit. So don't waste your time on the simplifying. We also learned how to take the derivatives of the exponential functions. Oh, and sorry, by the way, you'll notice that I didn't do any questions where the base wasn't an e. I will not expect you to take derivatives of functions that are log base 2, log base 3, even though that was something we did study in that chapter. So keeping with the same theme, if we add something like e to the 3x plus 4. Now, e to the 3x plus 4 is the natural exponential function. And of course, the rule for that one is very simple. If you recall, the derivative of e to the x is itself. So the derivative f prime of e to the 3x plus 4 is going to be e to the 3x plus 4. But remember that you always have to multiply by the derivative of the argument. So we take the derivative of 3x plus 4, which would just be 3. And I thought we'd do one more example. It's possible to actually combine our two functions in this unit. Suppose we had something like the function f of x equals e to the x times the natural log of x. So once again, we have a product rule. And I thought this was a good question to finish off with because it basically just summarizes your rules. When you take the derivative of e to the x, you get e to the x. The argument would have a derivative of 1, so we don't have to worry about it. Then you'd multiply by the natural log of x. I'm using the product rule here. Take the derivative of the natural log of x, which would be 1 over the argument, times the derivative of the argument, which again is 1, times e to the x. Okay, so this part of the exam, section 4, is going to get at your understanding of the basic rules of taking the derivatives of the natural log and the natural exponential function. So then, just to finish off our study of logs and exponents now, let's look at an application question. So to finish up our study of logs and exponents, we're going to look at an application. Just like previously in this course, every time once we learned how to take the derivatives of various functions using rules, we then turned our attention toward the applications. One of the applications we looked at, if you recall, was the concept of a related rate, a rate of change of a function. So what I'm going to do on your exam is I'm going to have you do a related rate problem involving logs and exponents. So what I've done here is set up a problem. It says the mass of a radioactive substance M in micrograms after time t in days is given by the following function. So you'll notice that our function is an exponential function. We have a base e, and the variable is in the exponent. The first question is not a calculus question. The first question simply says, find the mass at 50 days. So that's saying to you, take your mass function, replace the time with the time of 50 days, which means you would go 300 times e to the negative natural log of 2 over 140 times 50. Now really this question is just an exercise of practicing on your calculator. So you want to make sure you do this. This is the argument. You're raising the number e to this number right here. This is just a single number. So on your calculator, depending on how comfortable you are working it, you could just enter 300 times e, hit your exponent button, and then type in this value right here. If you do this, you'll get approximately for an answer 234.2 micrograms. Okay, so really what I'm doing with that question is just making sure that you understand how to access the exponential or the logarithmic features on your calculator. So that's not a calculus question. The next question, however, says find the rate of change. So hopefully by now you understand that the rate of change of a function is its derivative. So this question says find the rate of change at 50 days. So what we're looking for here is m prime of our function. So we need to take the derivative. When we take the derivative of this function, it's not nearly as complicated as it appears. The 300 is a constant, so the 300 would just stay out front. And the nice thing about the exponential function, if it's a base e, is the derivative is itself. So the derivative of e to this argument is going to be e to the same thing. But of course, you have to multiply by the derivative of the argument. Now again, it appears more complicated than it really is. You recall that if you have a number in front of a variable, like if you have 4t, then the derivative would just be 4. T is a linear function. Well, this number right here, negative natural log 2 over 140, that's just a constant being multiplied by time. So the derivative would just be negative natural log of 2 over 140. And then finally, the question wants us to find the rate of change at 50. So m prime at 50 is going to be 300 e to the negative natural log of 2 over 140 times 50, which, by the way, you've already calculated up here, and then times negative natural log of 2 over 140. So once again, it's not that complicated. It really comes down to your ability to use a calculator. So you want to make sure you practice that. And also the units are important. In this question, you were finding the mass, so it was just micrograms. In this case, you're finding the rate of change of the mass. So the answer works out to be approximately negative 1.16, and your units would be micrograms per day. So the first question simply told us how much of the substance was around at 50 days. This is telling us that at 50 days, the amount of the substance is decreasing at a rate of 1.16 micrograms per day. Now that we've completed the first part of the unit, logs and exponents, your test will now move on to the second half of the unit, which was the study of trig functions. So I've got here part B, and this is how I'll set your test up too. I will separate the parts so that you can clearly concentrate on logs and exponents for part A, and now you can turn your attention to the trig functions. The first thing we're going to look at with the trig functions are their limits. This isn't going to be a very substantial part of the test, but I do want you to understand especially the fundamental trig limit. You may recall that there was a limit that said the limit as x approaches 0 of sine x over x is 1. That's probably the most important limit in that unit. What I'll have you do in the test is just show me that you understand that particular limit and how to manipulate it. So for example, a question might look something like, what's the limit as x approaches 0 of sine 3x over x? And of course, the strategy here is we need to get the argument to be the same as the denominator. We know that this part right here, this x, has to be identical to this part right here. If that's the case, then the limit is 1. So what we have to do here is we recognize that this is 3x, so we have to get the denominator to be 3x. So we're going to multiply by 3 over 3. And of course, now that I've done that, I can take this 3 in the bottom and combine it with the x. So now we're going to have 3 sine 3x over 3x. And then this part right here is now our fundamental trig limit. So the answer is just going to be 3 times 1, or 3. Your textbook does get into a lot more of complicated questions. They're good for practice, but as far as your exam is concerned, I just want you to be able to show me that you understand the basic fundamental trig limit. So I wouldn't take it any further than that. Once we had the limit under control, we were able to develop our rules. So the next step on the exam would be to show me that you can differentiate a trig function. And again, you will not have to simplify. I do expect you to know all 6 rules, the derivatives of sine, cos, tan, secant, cosecant, and cotan. And so make sure that you're familiar with all 6 of them. There was a pattern we talked about. You might want to have a look at that pattern as a way of helping you remember the rules. I'll just run through a couple of examples for you here just to get you back thinking about it. But for example, I could have something like f of x equals negative 3 sine 2x. And the question would be asking you to find the derivative f prime. So in this case, the negative 3 is a constant, so the negative 3 stays out front. You have to know the derivative of sine. The derivative of sine is cos, and the argument never changes. So the derivative of sine 2x would be cos 2x. And then just like with the logs and exponents, you always take the derivative of the argument. So you have to multiply all of that by the derivative of 2x, which is 2. And again, I really mean it when I say don't simplify. On an exam, just leave your answer like that, and you'll get full credit. You may want to combine the 2 and the 3 and make it a negative 6, but it's not necessary to get full credit. So don't waste time doing that if it's not necessary. I'll just run you through a couple more examples. One that I like to make sure we talk about is what happens if you have an exponent, like what if you had the function f of x equals cos squared x? I believe the key in whenever you have powers is to rewrite the question in the following way. So cos squared x really just means cos x all squared. Once you've written it like that, then the derivative is simply your power rule. The power rule says we have to multiply the 2 out front. So 2 cos x, subtract 1 from the exponent, and then multiply by the derivative of what's inside the bracket, which would be the derivative of cos, which is negative sine x, times the derivative of the argument. But in this case, the argument is simply x, so the derivative would be 1. And that would be your answer. And again, there's no need to put the 1 here, and this negative can be moved out front. The brackets aren't necessary once that's done, but you do not have to do that on the test. I know there's a tendency to want to do that, and if you do it, I'm not going to penalize you for it. Obviously, that answer looks a little nicer, but I really want to stress that that is not necessary in order for you to get full credit. So whether you choose to do that or not is up to you. We'll do another one here. What if we had the function f of x equals cosecant of root x? So in this case, the exponent isn't with the trig function. The exponent is with the argument. This would be cosecant x to the 1/2. The reason why I picked this question is there's a big difference between cosecant x all to the 1/2 or just cosecant x to the 1/2. In this case, the argument is x to the 1/2. The cosecant function itself is not being rooted. So now we would take the derivative f prime. The derivative of cosecant is negative cosecant cotan. The argument never changes. So this will be negative cosecant x to the 1/2 cotan x to the 1/2. And then, of course, you always got to multiply by the derivative of the argument. In this case, the argument isn't just x, it's x to the 1/2. So we have to use our power rule. And that would be our answer right there. And I guess finally we'll do an example, again, just to show you that we can combine rules. You could have something like f of x equals 3x tan 5x. So the purpose of this question is that you recognize that you have a product rule. If that was just a 3, then it would be a constant. But it is a 3x, so we have to use the product rule. So the derivative of 3x would be 3 times tan 5x plus, now the derivative of tan is secant squared. So this will be secant squared 5x times, we always take the derivative of the argument, which would be 5, and of course times 3x because of the product rule. Now I didn't do an example of all 6 trig functions. I only picked 4 different ones, but I think you can see what the patterns here and what's going on and how they're done, and you can maybe practice a few of the other ones yourself. So we'll finish off with some applications. So we'll finish off our review of trig with a look at a couple of application questions. And again, the reason why I've selected these two particular questions is that they'll be very similar to the ones that you'll have to do on your exam. The first question was an application that we did earlier on in the year where we had to identify the local extrema of a function. If you recall, local extrema are max and min values. As a curve rises and falls, we're looking for the values of those points and also whether or not they are max or mins. So the question says, find the local extrema of a trig function f of x equals 1/2 x plus sine x. You'll notice that we're only asked to look between 0 and 2 pi. This is a sine wave and it's going to continue forever, so we would actually have an infinite number of extreme values. We're only looking for the ones between 0 and 2 pi. And then we want to classify them as either max or mins. So if you recall, extreme values will occur wherever the derivative is 0 or wherever the derivative doesn't exist. So we need to first of all differentiate. So if we take the derivative of 1/2 x is 1/2, and the derivative of sine x is cos x. So there's our derivative. Now that derivative would not have any values where it would not exist. There's no restrictions on the domain, so we're simply going to make our derivative equal to 0. Wherever our derivative is 0, our graph will have a horizontal tangent, and we will have an extreme value. Now, in order to do this, you have to know how to solve a trig equation. So what we're going to do is we're going to subtract the 1/2, and we're going to get cos x equals negative 1/2. Now, at this point, it depends how well I guess you understand your knowledge of trig, but what you're looking for is an angle between 0 and 2 pi, so one revolution of a circle, where cos is equal to negative 1/2. So first of all, we have to identify the quadrants. Cos is equal to negative in quadrant 2, so we could have an angle x in quadrant 2 where cos was negative 1/2, and we could also have an angle in quadrant 3 where cos is negative 1/2. Cos is positive in quadrants 1 and 4 and negative in 2 and 3. So we're going to expect two answers. Now we need to know what's called the reference angle. The reference angle is the angle that the terminal ray makes with the x-axis. So we need to find that value of alpha. And here's where you need your calculator. So on your calculator, you would just go alpha equals cos negative 1. And when you enter a trig value on your calculator, you never enter the negative value. The negative simply tells you the quadrant. So you would just enter cos negative 1 of 1/2. And your answer will be, you should be in rads, sorry. This is between 0 and 2 pi. So you want your answer to be in rads. You should get, if you're in degrees, you'll get 60 degrees, but you should get pi over 3. Pi over 3 is equivalent to 60 degrees. So this angle right here, this angle is going to be 1 pi backed up pi over 3. So we're going to get 2 pi over 3, or 120 degrees. And our other answer would be down here at pi plus pi over 3, or 4 pi over 3. I find that a lot of students, the difficulty they have in calculus in this section is simply their knowledge of trig. You have to be pretty comfortable working with trig equations, and hopefully this example helps a little bit. So that means we're going to have two extreme values. The extreme values will happen at 2 pi over 3 rads and 4 pi over 3. But the question does ask us to classify. Classify means determine whether they're max or mins. So you may recall we took something called the second derivative test. If we take the second derivative of our function, the derivative of 1/2 will be 0, and the derivative of cos is negative sine. The second derivative test tells us that if we plug our extreme values in, if you get a negative answer, you'll have a local max, and if you have a positive answer, you'll have a local min. So we need to plug in our critical values. So we need to plug in 2 pi over 3 into our second derivative. So negative sine 2 pi over 3. Now you can use a calculator for that, but I'd like to try to help you understand it at a deeper level. 2 pi over 3 is in quadrant 2. If you take the sine of an angle in quadrant 2, it's a positive answer. So I really don't care what the answer is. I just know it's positive, and then there's a negative in front, so this is going to be less than 0. Because it's less than 0, or negative, that means at this point, 2 pi over 3, this point is a max. So our curve has reached some kind of peak at 2 pi over 3. And we do the same thing with 4 pi over 3. Negative sine 4 pi over 3. 4 pi over 3 is in quadrant 3, and in quadrant 3 sine is negative. So the two negatives will cancel, and we'll get a greater than 0 answer or a positive answer, and so this is a min. Okay, so we found both of the extreme values, and we've classified them, which means we've determined whether or not they're max or mins. And for our last example, we're going to do an application of velocity. You may recall we did a section in this course on velocity and acceleration. We have the position function of an object. We're told that a particle is moving horizontally, and its position s is given by the following trig function, where s is in centimeters and t is in seconds. The first question says, find the position at 3 seconds. Well, the position is just s, so we're being asked to find s at 3. So that would be 2 sine 3 minus cos 3. You'll notice that we're plugging in a real number 3.
Sorry for the interruption. Can all the grade 9 teachers who took t-shirts please read their email immediately? Thank you.
Sorry for that interruption. There was an announcement. Notice that the number 3 is a real number. So when you plug 3 into this function, you have to be in rads. 3 is not a degree, it's a real number. So on your calculator, when you type this in, if you're in degrees, you won't get the right answer. So make sure you're in rads. And if you type that in, you'll get a value of approximately 1.27 centimeters. So what that would mean is this object is moving horizontally, so it's moving along a horizontal line. And at 3 seconds, its position is just to the right of the origin, 1.27 centimeters. So all we're doing in the first question is finding the location of the object. The second question, though, is saying how fast was the object traveling? In other words, what is its velocity? Well, of course, velocity is the derivative of position. Velocity is ds dt. So we're going to take the derivative of our function. So the derivative of 2 sine t would be 2 cos t, and the derivative of cos t would be negative sine t, so we'll get plus sine t. So that function would represent the velocity of that particle at any moment in time. So we want the velocity at 3 seconds, so we plug 3 into our function, 2 cos 3 plus sine 3, and your answer is negative 1.84. Now again, the units are very important. In this question, you were just finding position, which was centimeters. In this case, you're finding the rate of change of position, or velocity, so this would be centimeters per second, and the negative just indicates it's moving to the left. So by analyzing this particle at 3 seconds, we know that it's located just to the right of the origin, and it's moving back toward the origin at a rate of 1.84 centimeters per second. So that wraps up our study of Chapter 7, the logs, exponents, and trig functions. And hopefully, if you work through this review that I did with you, hopefully it'll help you on your exam.